Okay, so welcome back. And in this lecture, I'm going to give you a little overview of linear programming algorithms and give you a sense of their history. Obviously, this is something on which I'm not very well versed in, but I will try and give you a sense of the long history of linear programming, and this combines many streams of thought coming from areas as diverse as logic, computer science, operations research, and there are many streams of thought that converge to come up with this very rich theory of optimization. And oh, I completely forgot engineering. Control theory, for example, is a big contributor to optimization. So I cannot give you an entire history of what's happening in all of these areas, but let me try and give you a brief history of linear programming. Okay, so linear programming started off from logic. People were very much interested in solving systems of linear inequalities because people were very much interested in automated reasoning. And linear inequalities, theorems involving linear inequalities, was one area where it was thought that you could have algorithms that automate the reasoning. And there was very early work by Fourier, and we know some of that work today through a technique called the Fourier-Motzkin elimination algorithm for solving systems of linear inequalities. And this, in symbolic logic, is called linear arithmetic. Obviously, the Fourier-Motzkin algorithm is not very practical. Often it's exponential time in practice, but it was a very early example of people's attempt to solve this problem. Okay, and linear arithmetic is quite practical. There are actually solvers like Z3 from Microsoft that aim to solve these kinds of problems that come from logic, but to us they look a lot like linear programs, and they try to solve this efficiently. And this is a very interesting area which still continues. It's a very interesting tradition that still continues in parallel. A lot of linear programming work was done during World War II due to the problem of optimally allocating resources. So the earliest kinds of linear programs that were solved were linear programs that allocated peoples to tasks. So you had a bunch of people, a bunch of tasks, and you wanted to allocate the person to a task where the person was most qualified to do the task. And the kinds of problems people solved were really hard to solve by hand. And efficiency was a very important thing during those days. And this was also and this is not a coincidence really, that these were also the days when the first electronic computing machines started coming out. The first electromechanical machines for computing started coming out when people were starting to be interested in these kinds of problems. Two big names stand out from this era. Kantorovich, who won the Nobel Prize later on, worked on these problems in the USSR in the 1940s, and George Dantzig and his team worked on these problems from in the USA. And their publication dates do not say anything because a large amount of this work was done during the World War II when things weren't that easy to publish right away. Okay? And the main algorithm for solving linear programs, and the algorithm on which we will spend a lot of time in this class, is called the simplex algorithm. Many people say it's called simplex because it's simple, but it has nothing to do with simple. Simplex is a kind of a polytope. Okay, and it has a very strong relation to simplicis. Okay, and the simplex algorithm was the first algorithm published for solving linear programs. This was published by George Dantzig, who is rightly credited to be the father of this field. He has done so much work and he has contributed so much to these fields that what we are studying is directly the work of George Dantzig. He published his first paper in 1947 as a technical report that was subsequently republished, and there are lots of books by George Dantzig on this topic. I highly suggest that you acquire a copy of them if you are really interested in this area. I mean, you would like to see things from the original creator's mouth, then it's very important. For me, I have a very small personal connection. So here is a photo of me with George Dantzig taken many years ago. It's a long story how this picture got taken. I personally do not know the great man, but somehow I have a picture of him, and I'm very proud of this picture, I should say. Okay, so how does the simplex algorithm work? Well, we need to visualize the simplex algorithm because it's very important to see how it works. Okay, let's take a problem that we encountered previously, and let's take the feasible region for that problem. Okay, and we also convinced ourselves in a previous video that the solution is right here. Okay, and the way simplex works is through a hill climbing search. in the following way. What simplex is going to do is it's going to jump from vertex to vertex, and these corners are called the vertices, and simplex is going to land from one vertex to another vertex. Okay, and the way it does is each time it's at a vertex, suppose it starts from the vertex 0, 0. Each time it's at a vertex, it tries to go to a neighboring vertex. So in this case, it can either go here or here in a way that increases the objective function. So what it tries to do is to make sure that this guy never decreases. So it's going to try and keep it increasing and increasing and increasing until it can't be increased anymore, and then it stops. So that's how simplex works. So a run of simplex can go from here to here to here to here. So it skips around on the boundary of the polytope, on the boundary of the feasible region, until it gets to a solution, and then it detects that no further improvements are possible and prints the answer. Okay. If you want to learn about simplex, this is what's going to happen, and this is what we are going to spend the next 3 to 4 weeks trying to understand intimately. Very good. Okay. And then simplex was much improved by considering duality theory. And duality is something that we will also spend some time, quite some time learning, and it's very important optimization. Understanding the dual is often very important in solving an optimization problem. And this comes from early work by Lagrange. It's known, it's called the Lagrangian dual for a reason. Okay, Lagrange was a French mathematician, okay, a long time ago, and it comes from very early work by Lagrange, but it was formally developed very soon after Danzig published linear programming by John von Neumann, again a huge name in computer science, mathematics, game theory, economics. I mean, there's no single field, physics. Von Neumann was everywhere in those days, and he's the prototypical genius, and he contributed a lot to this field through duality. And this was generalized by Karish-Kuhn and Tucker to give you what we call in optimization today as the Karish-Kuhn-Tucker conditions, or short for KKT conditions. And we'll see this as well as part of this course. We'll see KKT conditions for linear programs and use them to form other methods for solving it. There is one unfortunate fact about simplex, is that its complexity is exponential time in the worst case in the size of the problem. So it can take a large amount of time to finish, and Klee and Minty showed an example of one case where a simplex with a particular pivoting rule can take a large amount of time to finish, exponential amount of time. But there has been a large amount of work that's already been done that shows that on the average, simplex works really fast. It works in polynomial time. Okay? And in particular, there's work by Spielman on something called smooth analysis, who finds, and he found like very interesting ways of proving this and making this formal, that the expected case running time of simplex is polynomial time. And there are many others who have given results that make us believe that simplex is actually a very practical algorithm for the problems you encounter in practice, but much remains to be understood as well. Okay, in terms of polynomial time algorithms, this problem was open for more than 40 years until Leonid Khachiyan came up with the ellipsoidal algorithm. And this algorithm is the first polynomial time algorithm. Many people had suggested this algorithm before Khachiyan, but this contribution was mainly to show that the ellipsoidal algorithm solves simplex in polynomial time. But the interest in this algorithm is mostly theoretical. To my knowledge, no tool implements the ellipsoidal algorithm. What tools really implement these days are either simplex or interior point methods. So simplex still remains valid in spite of its exponential time complexity, and the other class of methods are interior point methods. These are based on ideas that go back to Isaac Newton, really old ideas in mathematics that were first brought to linear programs by the work of Karmarkar in the 80s. But interestingly enough, before Karmarkar came with interior point methods for linear program, people knew about interior point methods for nonlinear programs long before Karmarkar came up with linear programs. And if you want to learn about interior point methods and nonlinear optimization, there's a great book by Wright and Nosedal, which is really good, and highly recommend this book. Okay, so applications of linear programming theory are too numerous to list exhaustively. Okay, everyone who does their PhD in engineering, some form of control, some theoretical computer science, has to do something with linear programs. It's inescapable, really. The major application areas are operations research, where it turned out to completely revolutionize the way things were done. computer science, if you take any kind of algorithms, and more recently machine learning, automated reasoning, robotics, in all these fields, linear programming is a central algorithm. It's this one case which is solved, which is beautiful, which everyone understands, and then comes all the bad complexity and everything else. Okay, so linear programming remains at the core of many of these things. In engineering, optimization and control theory are very closely linked. You cannot do control theory without understanding some amount of optimization, especially if you're interested in nonlinear controls or more advanced control theory. And linear programming turns out to be the fundamental basis of understanding the more complicated techniques people use in optimization and control theory. So again, it's at the core of whatever you do. And if you're an engineer or if you work in one of these fields, chances are linear programming is something that you need to know, you need to understand before you move forward. Very good. So in this course, we are going to study simplex algorithm. So we are going to spend a lot of time with the simplex algorithm because it's a very simple algorithm at its core. Okay, maybe it's meant to be called simplex because of that. But it's also very deep. It's mathematically very, very deep. And understanding duality and those kinds of concepts become very easy if you understand simplex. So we are going to work with simplex. But we are also going to study interior point methods. We are going to come up with some algorithms for interior point methods. And it's very interesting if you understand simplex, if you understand duality, then understanding these is not that complicated. Of course, proving their polynomial time is complicated, but implementing and understanding how they work is not complicated at all. So we'll do some of that. And that's the first part of this course. The course is also going to have a lot of applications. Okay, we are going to try and motivate everything we do with lots of applications. And eventually, we are also going to study some integer linear programming, but mostly as a way of augmenting linear programming solvers with ability to treat integer variables. Okay, so that's what we have on the menu for this course in the next few weeks, and I'm hoping that it will be exciting and we will have a lot to say about these topics and a lot to think about. Thank you, and I will see you in the next lecture.